folks. Welcome back to Physics with Captain Rod. I'm making this one to help you with let's see, what are we, 3-3, number 10 here. And this is about a bug that's sitting on, it says some sort of rim. So here's my bug, and this is my rim, and it's rotating. It's got an angular velocity to it. Now, the diameter is given, and that means the radius also is given. I like to work in terms of the radius. So that's a given number in the problem. Now it says it accelerates from rest to 79 revolution per minute in 3.6 seconds. Your numbers might be different, but I would definitely start with a velocity graph. Now this is an angular velocity graph. Angular velocity against time. This is how we study motion typically. So we got here what's typically called omega, the angular velocity, and then again against time here. It starts from rest, so the first point on that graph is here. And then it gives a number, 79 revolution per minute. There's a couple things to do here. If you had 79 revolution per minute, I would probably convert that to radian per second. So remember, there's 2 pi radians in 1 revolution, and there's 60 seconds in 1 minute. So now that should allow you to fairly easily calculate that in radian per second. And they give a time, so your graph will now look like this, some number for the time, and a number given here, and we'll assume constant acceleration. Now, the part that says, what is the magnitude of the tangential acceleration? So your tangential acceleration is change in speed over change in time. So it's the change in your magnitude of your velocity. What you need to do is calculate the speed of that object here. And actually, this would have been just fine unit-wise for that, the 79 revolution per second. So the final speed, let's put V final. If you take the 79 revolution per second, right, and you multiply that by 2 pi r in, put units of distance. This has units of feet per second or meter per second, depending on your unit. This wants meter per second, so put that in meters. And this will come out now to a number with units of meter per second. That's going to be your V final. And that's going to be the speed. Then your tangential acceleration will be that divided by your time. Part B, where it says when the bug is at final speed, what's the tangential velocity? That's this number we just calculated. We needed that for part A anyway. Okay, and then it says 1 second from starting from rest. What is the magnitude of the tangential acceleration? So the tangential acceleration is change in v over change in t. If we assume constant, that's not changing. So just take this over this, and that should get that done. 1 second after the bug starts from rest, what is the centripetal acceleration? Okay, now that's a different story. So the centripetal acceleration is equal to v squared over r. So you need to know the speed, the v, at 1 second. Now, once you have the tangential acceleration, that's going to be some number. Just put a sub t here. And that's equal to changes in speed over changes in time. So put in 1 second to calculate your change in speed. Then you're going to use that here to calculate your centripetal acceleration. For part E, where it says 1 second after motion, what is the total acceleration? So a top view would be kind of nice for this. Do a quick sketch here. So let's say the bug starts out here from rest. The motion diagram is kind of looking like this because the bug's moving faster and faster and faster. At the instant I'm drawn, at the instant shown, the bug has a tangential acceleration and a centripetal. You calculated those earlier in the problem. And then the net acceleration is the sum of the two, the vector sum. Remember, when you add vectors, they have to be tip to tail. So you might do something like take the tangential and draw it here, draw your net, use Pythagorean theorem. So hopefully that'll get that problem done. Again, I'm always available if you need help with it. Have a great day.